I'm Belhadj and this is my video lab report. This lab examines the motion of a falling object. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly. Then the observational model must be compared to the computational model with gravity only and the computational model that takes into account both gravity and drag. The results highlight how the more forces that affect the object are taken into consideration, the more accurate the predicted model becomes because there is less deviation in the computational model depicting gravity and drag rather than solely gravity. Newton's second law states that the force of an object is equal to its mass times its acceleration. In other words, the force is equal to the rate of change of momentum. The law relates to the total interactions between the system and surroundings to the changes in the motion of the system. Gravity is the force of attraction that exists between any two masses. It is measured by the acceleration it gives to freely falling objects. At Earth's surface, the acceleration of gravity is about 9.8 meters per second squared. Drag force is the force that opposes the relative motion of an object. It increases as an object speeds up. Then it becomes equal to the force of gravity and the object falls at terminal velocity. Turbulent drag is always proportional to the square of velocity. The net force is the sum of all forces acting on an object. So in this lab, it will be the sum of the gravitational force and drag force. So this is a video of me dropping a volleyball from rest. In this experiment, the system is a volleyball and everything outside of the system is referred to as its surroundings. Here we can see the time and position data values. Here we have the code for the first computational model that only takes into account gravity. Here is the mass of the ball, 0.27 kilograms, and here's the initial position and the initial velocity. And then we move on here, and the last time frame is 0.367. And then we've calculated the net force. We're only taking into account gravity, so this is the equation, and updating the velocity using this equation and updating the position of the object. And then we run the program and we get this position versus time graph and these data values. And then we move on to our second computational model, which takes into account both gravity and the drag force. And there are two changes within this code. First, we have the proportionality constant, which I've estimated through trial and error to make sure that the predicted model's last position is the same as the observed model's last position. And then the second change was the net force, because now we're taking into account the force of drag. So this adds both the gravitational force and the drag force. And then we run this program and we get this position versus time graph. As you can see, the computational model that only includes gravity starts to deviate a lot after the beginning. This is because it is not taking into account the force of drag that occurs on free-falling objects. As the greater an object speeds up, drag increases. The computational model that accounts for both gravity and drag is much more accurate, which shows that the drag force plays an important role in determining the motion of a free-falling object. Although the computational model of drag and the observed model are almost completely aligned, there is a tiny bit of deviation in the middle, and that might be due to the estimation of the proportionality constant not being completely accurate, as it resulted in a final position that is extremely close to the observed final position, but not the exact same value when it comes to each decimal point. Which model predicted a terminal velocity? A terminal velocity is reached when the drag force is equal and opposite to the force of gravity. Only the second computational model took into consideration the drag force, so it is the model that predicted a terminal velocity. In the model, it shows that it started to flatten and become a bit more linear, which can show that the object is approaching terminal velocity. The net force of an object becomes zero because the drag of the object cancels out the force of gravity. What if the object was initially thrown downward? Would the terminal velocity be the same or different? An object's terminal velocity only depends on the velocity needed for the drag force to be equal and opposite to the force of gravity. The initial velocity is not relevant as it would still approach terminal velocity in the same way. Terminal velocity is specific to the object and is not dependent on its initial velocity. However, it may reach terminal velocity more quickly than if it was dropped from rest.